At subsets and set operations. So the universal set for any given situation is identified by the letter U. This is the set of all objects that are reasonable to consider for that situation. So once you define the universal set in a specific context, then we have to start thinking about it as elements. So we're going from the big picture to the smaller picture. Then the only elements we can use to define other sets would be integers from 1 to 8 in that example given. We like to use Venn diagrams as a way of visualizing a set and then relationships between groups of items. And this was named after John Venn, so this is an example of a Venn diagram. It's a visual way to obtaining cardinality of sets. The complement of a set, which we show as A with the quotation mark, I guess not quotation mark, A with the apostrophe, is the set of all elements that are not in a set. So if I am saying the set is even numbers, then 3 would be the complement of that set because it is not an even number. So it's kind of like playing devil's advocate a bit. And when we talk about a Venn diagram for a complement, then it's all the things that are inside the rectangle but are not inside the circle, because everything inside the circle belongs to my set. So if I look at the example here, I have U is V, W, X, Y, and Z, and A is W, Y, Z. I want to find the complement of A and then draw the Venn diagram that uses it. So if I look at the elements that are in that U, I can cross out everybody who also lives in A. So then if I look at not A, what are the values in U that are not in A would be V and X. There's no element in the universal set that is not in the universal set, because by definition, the universal set is everything. So that means the complement to that set is empty. Every element in a set could be written in a more specific manner, which is a subset. So the symbol we use for a subset is going to be the union, but the sideways union with the bar under it. So every set is a subset of itself, meaning if I have a list of numbers 1, 5, 10, then 1, 5, 10 is a subset of itself. So it's almost like you have to think about the set that is equal, and then there you go. And then the empty set is a subset of every set. So this is where you can get lost in Alex a little bit, is because you have to remember that if you're listing all the subsets, you have to recopy the set itself, and then you also have to recopy the empty set. So if I'm finding all the subsets of a set, I have cold and flu. So cold and flu is a subset of itself. Then I have the empty subset, and then I have plain old cold and plain old flu. So the first the first and the last one are easy to miss. Proper subsets are going to be subsets that are not equal. So such that A is not equal to B. So I'm taking out that first layer. So if I look at this Venn diagram, I have all the items in A are found in B except for the number 5. And then the numbers 2 and 4 from set U don't belong to either one of those, but they are still a part of the universal set. So I'm going to put them outside of the circles. If I want to find all the proper subsets of this list, proper subsets mean it doesn't include the set itself, so I don't write that. And then I'm going to write every permutation of the list. So 2 items of the list, and then 1 item of the list. Since order does not matter, marketing English and English marketing are not seen as 2 unique answers. So you can't reorder the items to create more proper subsets. So in this example, let's decide if each statement is true or false. So in part A, 1, 3, and 5 are in the second set. So it is a subset and it's true. And B, if I go back up here to B, A and B is a subset of A and B, but it's not a proper subset, which is what that notation is indicating, so it's false. In part C, I have x values such that x is greater than 10 is a subset of the natural numbers. Well, that's true. In part E, there's 2 Great Lakes, and so they said that Lake Erie and Lake Huron that statement would be true. Oops, I keep scrolling ahead of myself. And then it would be false because there's more lakes. And then the empty set is a proper subset of all sets, so that would be true. In V, if I look at those 2 sets, V is an element of the first one, but not in the second one, so that's going to be false. And then the element on the left in part H only has 1 element, 0, and the empty set has no elements, so it's going to be false. So what's important is to remember the empty set is not the same as 0. The empty set means your list is empty. So if you just left the grocery store, assuming they had stock of everything, then you don't need anything else at the grocery store. So your grocery list is empty, like the empty set. The number of subsets in a finite set is found by utilizing 2 raised to the number of items minus 1. So if I have a set with 4 numbers, it's going to be 2 to the 4th power, calculated that, and then minus 1. If I want to know the number of just subsets and not proper subsets, then that's going to be 2 to the 4th power. So let's look at this example that we're given. I've got ace, king, queen, jack, 10, 9. So that means there are 6 elements in the set. So I have 2 to the 6th power subsets, and then I subtract 1 from that to get the number of proper subsets. And the reason we're doing that is because when we find a proper subset, I have to remove the original set from the equation. And the intersection of sets basically means the overlap. But we actually read it as and. So A and B would be combining the 2 sets. So for instance, if I have A and B here, I'm looking at the combined elements in both sets. So what values are contained in A and B? So in this case, 14 and 15 are in both. So then that would be A and B. And if I look at the Venn diagram, you should see the overlap there. So they're overlapping for those numbers. Let's take a look at this example. So find each requested set, A and B, B and C. Ooh, and this is tricky. A and B and C. So if I'm examining this, A and B both have nausea and nervousness. B and C both have nausea, blurry vision, and fever. And the only thing that's in all 3 groups is nausea. So a disjoint set is going to be the intersection of 2 sets that's the empty set. So meaning that there's nothing really common there, it's going to be called disjoint. So if students who stop attending class midway through the term and the student earning A's are disjoint, it's because you can't be a member of both. Nobody is in common with both sets. So when we see this, we actually separate out the circles in the Venn diagram because there's no overlap. There's no values that cross over between group A, or set A, and set B. So the union of 2 sets, this is different than the A and B. Notice the U is upside down, or the N, however you want to say it, the union symbol. And so they're in either set A or set B. So think about if I say bring socks or shoes. Either one would be acceptable if you brought it. So it really means putting them together. So if I have set A and I have set B, I'm going to combine my list. But I'm not going to write values twice. So even though 5 belongs to both sets, I don't write 5 2 times. So a great example of this would be the one that's given here with finding unions of A and B, A and C, or A union B union C. So if I'm looking this from example 16, so I'm referencing that earlier list of symptoms. A union B would be nausea, night sweats, nervousness, dry mouth, swollen feet, all of it. So I'm combining all of the elements of A with all of the elements in B. So A or B. A or C means take all the elements of A, combine them with the elements of C. And then A or B or C means take all of A, all of B, and all of C. So let's look at doing set operations. In this case, it starts getting to be tricky because I need to follow order of operations. So first I'm going to do A or B and C. So in A or B, I'm going to combine all the things in A and all the things in B. Then I have to figure out what does that group have in common with C. So that would be dry mouth, nausea, blurry vision, and fever. Now let's look at all the things in B or C. So I'm making a complete list of all elements in B and all elements in C. I'm combining my list. And then I'm saying, what does A have in common with that? And A has in common nausea, dry mouth, and nervousness. And then for C, you would have A and B. So what things do A and B have in common? And then combine that with C. Another example of set operations would be looking at the complement. So remember, complement is anything that is not found in that original set. So what we should be aware of is when we're combining union and intersection with complements, as we are in this example, we have to be really careful and pay attention to where the parentheses are and whether the complement symbol is inside or outside of the parentheses. So first, before I can deal with the set operation, I need to find the complement of A. So what are all the items in the universal set? So all the items in every set list that are not contained in A. So I have all of those things. Then I have to find C, and I have to find all the items in C that are not in the universal set. Or all the items that are not, And then I can finally find it. So the key here is you're going to have to say, okay, I got to find the complement of A, which would be all the items that are in so make a list of all the combined sets, cross out everything that's in A. Same thing, C, make a list of all the items in all the sets, cross out everything that's found in C. And then I find, from there, I'm wanting to find the elements that they have in common. So what is also in the A and B set there? So the parentheses tell us that I need to do A and B first for part B. So I'm finding where does A and B overlap. Then I'm going to say, okay, according to all the lists, let me combine all the list of the sets together and then cross out nausea and nervousness. That's how I'm going to tackle that one. And then in part C, we also have the same reasoning. If I want to talk about set subtraction, this can be very misleading. The difference of two sets is the set of A that are not in B. So it would make sense to just cross out, I would think, the items from the set. That would be our instinct. So let's see if that works. So I want to start with A minus B. So I want to take the elements of A and remove anything from B that's in that list. And that's what I wind up with. To do B minus C, I go to set B, and I take anything out of it that's in set C. And then finally, in part C, I'm going to take the set A. I'm going to take anything out of it that's in B. I'm going to take that answer and then take out anything that lies in C.